Hello, welcome to the fundamentals of fluid dynamics. At first, you ask me why do we need fluid dynamics? We have learned a lot about fluid statics, we have learned about the fluid properties, and fluid dynamics is still a really important topic for all kinds of technologies. And even if we get a change now from um, combustion engine cars to maybe combustion engines, they have a lot of fluid dynamic problems, but even if we change now to fuel cells, to hydrogen fuel, we will have a lot of fluid dynamics problems. For example, if you have here a kind of fuel cell car, we have fluid flow at different positions. We have fluid flow of water, and we have also big problem of cavitation, of icing here. We have fluid flow of hydrogen, we have fluid flow of water. We have to cool the batteries, and we have to look also at the hydrogen tank, and we can have also turbochargers for hydrogen or for air. And that's all fluid dynamic problems. So we must have a close look at fuel cells now in future. And here you can see a fuel cell car, and our university already bought a fuel cell car, and you can have a look at this technology. And also filling the car with hydrogen is again a fluid dynamic problem. Here you see a filling station, and I think that's also a big advantage of hydrogen cars with fuel cells, if you compare them with normal electric cars, because you can charge them really fast. You can charge them in a filling station that is similar to a gas filling station, and all the technology is already here. So have a look at fuel cells, and we also want to make a short internship with you. And we have here this interesting windmills and wind technology, and we want to make CFD simulation of such a windmill. And so you have to so fluid dynamics is important for you if you look closely at the production of energy by wind, but also in storing energy. Fluid dynamics is an important topic. For example, here we have a fuel cell, and the fuel cell converts water to hydrogen by electrolysis, and you also have flow problems around the fuel cell. You have heating problems, you have cooling problems. So you need, at the production of the electricity, you need knowledge of fluid dynamics, and also if you look at the storing of the energy, and you will get fluid dynamic problems. Okay, so let's look at the principles of fluid dynamics. So you have a motivation. Fluid dynamic is really modern, is a really important topic, and the general principle of fluid dynamics is that you have a control volume. You have here a volume of air or of water, and you have forces acting on this volume. You have inertial forces, here, and you have compressive forces on this fluid. But you can imagine, if you have a fluid like a bubble, or like an area where water is, and if you now act with forces on this region, let's say on this region, the water will flow away, or the air will flow away. So you will always have an interaction of the fluid with the inertial forces. To describe this, we will divide the fluid into cells. We will define volumes, control volumes, and we will have here is an example of a control volume, and we divide the whole volume in such a control volume, and then we have boundary conditions, we have forces acting on the control volume, and we will have forces inside the volume that will influence the movement of the fluid. And important at the first step is you have to know a lot about geometries, you have to know how big such a volume is, how you can calculate the volume, how you can calculate areas around this volume. And in many cases it's also important, the problems are not always steady state. Steady state means you have a constant influence from the side here or from the side here, and non-steady state problems, if you have non-steady state problems, the force might change, or a velocity might change, velocity at the boundary condition. So if you have changing boundary conditions, you will also have a changing fluid flow after several time steps. Okay, I think you all know what this is in the weather forecast. And weather forecast, I think if you think about the weather forecast, you can describe fluid flow problems and the principle of fluid flow really in a good way, because what is important here, you see, you have here the Azoric Islands, you have here Iceland, and what you see on this map, you have these lines, you have these black lines, red lines and blue lines, and the blue and the lines that are isobaric lines, they indicate different pressure levels. So with the map of Europe, and maybe you can have a look at the conditions in your home region, but here I live in the center of Europe, and we nearly have always the same weather or very similar weather, and in general we have west winds. So the winds come from the Atlantic Ocean here, and Europe is mainly influenced by this kind of west winds. And why do we have west winds in many days? Because we have really high pressures here over the Azoric Islands, and we have really low pressures here over Iceland. And what will happen if we have high pressure here, low pressure here? The velocity will rise. The velocity will rise from the high pressure region to the low pressure region over Iceland, and this will cause the weather and the winds, and the winds will take the clouds with them, and then we have nearly always good weather here, and we have really often bad weather here in the upper region. Okay, so what is important here? Please always remember, the fluid will always flow from the high pressure region to the low pressure region. Okay, and how can we make this weather forecast? How can we produce a weather forecast? How can we will weather forecast more or less is really big and time-consuming simulation. It's a computational fluid dynamics simulation, and more or less a fluid flow simulation and a heat transfer simulation. And to do the simulations, we need really big machines. Here is a computer of the High Performance Computing Center in Stuttgart, and I've also made a lot of simulations on this computer center. And for example, here you can see fluid flow inside a coal-fired power plant. That's really similar to weather forecast. You have to calculate where the air and the oxygen should be, and where are the regions where we should inject the coal particles. So it's really, you can compare it. If you build a coal-fired power plant, this is really comparable with a weather forecast simulation. Or for example, here is a picture of a car, and it's a really good visualization of fluid flow around the car, and you can also imagine you can have higher pressures at some regions, you can have lower pressures, you can have turbulences, and so you can design the geometry of your car. Okay, but I showed you this really big computers of the High Performance Computing Center in Stuttgart, the HLRS. You can also find it on www.hlrs.de. But a lot of theory I teach you is really quite old. For example, I mentioned the Bernoulli equation in former lectures. Or I want to mention also Gottfried Wilhelm Leibniz. He lived in the 17th century, 18th century, and he also did a lot of simulations or it's called calculations for fluid flow problems, and he also had computers. He built his own computers. Now you ask me how he lived in the 18th century, how can he build computers? But they built this kind of mechanical computers, and they still exist, and they didn't do this for fun. You can imagine, if you have a look at the slides, they look really expensive, and in former times these computers were as expensive as the big computers today, and they also used them for fluid dynamics simulation, for computational fluid dynamics, and they had really similar theories as nowadays.